So good day, students, and welcome back to our next visual lecture. The topic that we're going to talk about, so in this lesson, the liquid solid phase diagram. Remember that we are still talking about the two-component system. But before I go into details about the solid liquid phase diagram, there are a number of points that I also want to make about our previous lecture. Remember that during the previous lesson, I think we were talking about the liquid phase diagram. I've said that, so when you are mixing two liquids, there are two scenarios that could happen. The first scenario is whereby those two liquids they become completely miscible in one another. Second scenario, so those two liquids they can be partially miscible in one. So when the mixture is completely miscible in one, we can have what we call the azeotrope. I think I have shown in the previous lecture that for the azeotropes, we can have two types of the azeotrope. The first one, we can have the higher azeotropes. The second one, we can also have the lower azeotropes. So those two azeotropes, they actually differ in terms of the phase diagram. So in case whereby we are having the partially miscible liquids, so this is the type of the phase diagram that one can see. So in this example, we are having an example about the temperature composition diagram for hexane as well as nitrobenzene. So in this diagram, as you can see, the region below the curve corresponds to the composition and the temperature at which the liquids they are partially miscible. So in other words, when we are having two liquids that are partially miscible in one, it means that we are going to have two phases. So the other thing that is interesting about this particular graph that we also have the point. So this point is called the upper critical temperature. So by definition, that the upper critical temperature is the temperature above which the liquids they are miscible in all proportion. So meaning that in this particular diagram, so above that particular point, it means that our liquids it will be completely miscible in one another. But below that particular point, it means that we are having a mixture that is completely miscible in one another. So moving forward, remember that I've just shown what is the upper critical solution temperature is. So this slide still continue to explain what I've said in the previous slide. The highest temperature at which phase separations occurs. So the other important point that I've also mentioned is that above this point, it means above the critical temperature, the two components they're actually fully miscible. But below the critical temperature, it means that the components they're partially miscible in one another. And below the critical temperature, it means that we have two phases. But above the critical temperature, it means the number of phases that we are going to have, we are just going to have one phase. So how do we explain this temperature at the molecular level? So on the molecular level, so this can be interpreted as the kinetic energy of each molecule overcoming molecular interactions that want molecules of one type to come close together. Okay, just like in the case of the azeotropes, whereby we're having the higher azeotrope and we're also having the lower azeotropes. So even for the critical temperature people, it is also possible that instead of having the higher critical temperature, but to have what we call the lower critical temperature. I think the case whereby maybe we can have the higher critical temperature of the lower critical temperature, it will also depend on the type of the liquids that maybe will be working with. Remember that like these liquids, like I've said previously, normally differ in terms of the boiling point. They also differ in terms of volatility. I think they also differ in terms of the density. In fact, there are a number of factors. I think, ladies and gentlemen, you can look into your textbook, maybe you can find some of the factors that will affect whether, or that will determine whether are we going to have the higher critical temperature or are we going to have the lower critical temperature. So for a system whereby we're having the lower critical temperature, it means that below this temperature, the two components, they will mix in all proportions. And above, it means that they're going to form two phases. So a typical example whereby we are having the lower critical temperature is whereby we're having a mixture of water as well as triethylene amine. So this is how the phase diagram or a composition of water as well as triethylene amine will look like. I think as you can see from the diagram, it's very clear that in this instance, instead of having the higher critical temperature, in this case, we are having the lower critical temperature. I think we can see that in this instance, it means that below the lower critical temperature, our mixture will be completely miscible in one another. But in this instance, it means that above the critical temperature, our mixture will be partially miscible in one another. And again, we are going to have two phases in this particular. Okay, some of the reasons that are provided in that case is that water and triethylene amine, they normally form a weak molecular complex. Hence, at higher temperature, the complexes, they break up and the two components, they become less miscible. So in other words, I think we can see that it is possible that one can have the upper critical temperature or one can have the lower critical temperature. But in some instances, it is also possible that within one system, we have maybe both the upper critical temperature as well as the lower critical temperature. So let's look at this particular example. So this is the temperature composition diagram for a mixture of water and nicotine, which has both the upper and the lower critical temperature. So I think this diagram is not completely different from what I have shown you. So even in this instance, it means that the points between the upper critical temperature and the lower critical temperature, at that particular temperature, it means that our mixture will be partially miscible in one another, in such a way that we are going to have two phases. But in this case, as we can see that above the upper critical temperature and below the lower critical temperature, it means that our mixture is going to be completely miscible in one another. In such a case that we will end up having only one phase. Okay, let's move to the next topic. So let's talk about the distillation of the partially miscible liquids. The question that we can ask is that what happens when we distill partially miscible liquids? What happens when you distill partially miscible liquids? Normally, a pair of the liquids that are partially miscible, often they form what we call a low boiling azeotrope. So there are two possibilities that can exist. The first one in which the liquids become fully miscible before they boil. The second thing that could also happen is that the other in which boiling occurs before mixing is complete. So these 2 points, people, they're very important. We are having two liquids. So these two liquids, they're partially miscible in one another. So if we are distilling them, what will happen? So those 2 points, very, very important. So we can have a scenario in which the upper critical temperature is less than the boiling point at all composition. So in this case, it means that our mixture will form a low boiling azeotrope. So in case whereby we are trying to distill our point, it's possible that we can have the low boiling azeotrope, and it's also possible that we can have the higher boiling azeotrope. So in case whereby we are having the low boiling azeotropes, so our temperature composition diagram will look something like this. I think you can go through your textbook, ladies and gentlemen, and read through about all these varying points. So the other scenario that we spoke about, like when you are boiling, when you are distilling partially miscible liquids, is whereby the boiling is going to occur before the two liquids are fully miscible. So this is the temperature composition diagram of that particular instant. So even for this diagram, ladies and gentlemen, just go through the textbook and read about what is going to happen. Okay, for our today's main topic, which was the liquid solid phase diagram. So in this case, remember that I was talking about liquid, but now I'm talking about liquid solid phase diagram. So there are some important knowledge that we need to have before we can go through this particular topic. So the knowledge of the temperature composition for solid diagram is very, very important. So because this knowledge normally guides the design of the important industrial processes, such as the manufacture of the liquid crystal display, as well as the semiconductor. So in case of the liquid solid phase diagram, we can have two different types of the diagrams that we can have. So one diagram, the temperature composition phase diagram for two almost immiscible solids, and they are completely miscible liquids. So this is how the phase diagram looks like. So you can go through your textbook and read through about this particular diagram. So this diagram, I think, is trying to explain what is going to happen at various points. So ladies and gentlemen, thank you for listening to this video and watching this. Thank you.